Galileo's inclined plane experiment, 1589. A revolution in understanding gravity. Galileo Galilei, an Italian scientist, philosopher, and mathematician, lived from the late 16th century into the early 17th century. His contributions to science not only transformed the understanding of the physical world but also fundamentally changed the way scientific thinking was approached. One of Galileo's most notable discoveries was his inclined plane experiment, conducted in 1589 at the University of Pisa, which became one of the cornerstones of modern physics. This experiment shook the prevailing scientific beliefs of the time and disproved long-held misconceptions about gravity. During this period, the scientific views of ancient Greek philosophers, particularly Aristotle, were dominant. Aristotle believed that when objects fell due to gravity, heavier objects fell faster than lighter ones. According to this view, a stone would hit the ground much quicker than a feather when dropped. This theory was widely accepted for centuries, shaping people's understanding of gravity and motion. However, Galileo set out to challenge this idea, deciding to test it through direct observation and experimentation rather than relying solely on theoretical reasoning. Galileo was deeply convinced that gaining a better understanding of gravity required more than just theoretical speculation, it required observation and experimentation. His inclined plane experiment was aimed at testing whether heavier objects truly fell faster than lighter ones. To do this, he built a ramp-like surface near the Leaning Tower of Pisa, which provided an ideal surface for rolling two metal balls down. Galileo observed these balls, which had different weights, to see if their descent times differed. The results of this experiment would prove to be revolutionary. Both balls, regardless of their weight, fell at the same speed. This observation not only disproved Aristotle's ideas but also demonstrated how scientific thinking should proceed. Galileo showed that weight did not affect the rate at which objects fell. Both heavy and light objects, under the same conditions, fell at the same speed. This simple yet groundbreaking discovery marked a turning point in the scientific world. Galileo's findings revealed that the forces of gravity alone determined the rate of descent and that weight had no influence on this speed. The historical importance of Galileo's inclined plane experiment goes beyond the results of the experiment itself. It also demonstrates how he developed the scientific method. Galileo believed that the foundation of science should be built on observational data and experimental testing, rather than relying on accepted theories alone. While other scientists and philosophers of the time often based their theories on logical deductions and philosophical principles, Galileo emphasized the importance of direct evidence. In this sense, his inclined plane experiment shows how Galileo applied the scientific method, by observing and testing nature's phenomena. Galileo's experiment had a profound impact, quickly sparking widespread debate. His findings challenged the prevailing views of the time, and many of his contemporaries were reluctant to accept them. However, his bold step not only changed the way we understand gravity but also marked the beginning of a new era in scientific inquiry. Galileo's focus on empirical observation laid the groundwork for future advancements in the physical sciences. Galileo's findings from the inclined plane experiment didn't just change the understanding of gravity in his own time, they shaped the future of science. The experiment had a direct influence on the development of Newton's laws of gravity. Newton's laws would later confirm Galileo's findings, providing a more comprehensive understanding of universal gravitation and the laws of motion. Galileo's discovery paved the way for a more profound understanding of the forces that govern the universe. Another significant aspect of Galileo's inclined plane experiment was that it showed how science is always evolving. Scientific knowledge is never fixed or limited to what is considered true at any given time. Each new discovery presents an opportunity to question prior beliefs and move toward a deeper understanding. Galileo's work in this regard was not just a simple observation of the physical world but also an illustration of how science itself should progress. The results of the inclined plane experiment demonstrated that science should be built on testable and observable facts, and not merely on theoretical speculation. Today, when we look back at Galileo's inclined plane experiment, we see just how profound and transformative his contributions to scientific thinking were. His groundbreaking observations not only shaped his own time but also laid the foundation for future advancements in the scientific world. Galileo's experiment represents a critical moment in the history of science, a moment when the world began to see the natural laws of the universe in a new, more accurate light. His approach to scientific inquiry, based on observation, experimentation, and evidence, continues to influence the way science is practiced today. Through Galileo's inclined plane experiment, we are reminded of the importance of questioning accepted ideas, seeking empirical evidence, and embracing new methods of understanding the world. Galileo not only changed the way we think about gravity but also demonstrated how science should evolve. His work remains one of the most influential moments in the history of scientific thought, and his legacy continues to inspire modern scientific investigation. Newton's gravity experiment 1687, unveiling the laws of nature. Isaac Newton, one of the most influential figures in the history of science, made groundbreaking contributions that changed the way humanity understood the natural world. Among his most significant achievements was the formulation of the laws of motion and universal gravitation. His work, especially as laid out in the 1687 book Philosophiae Naturalis Principia Mathematica, Mathematical Principles of Natural Philosophy, fundamentally altered the scientific understanding of gravity. While Newton didn't perform a single gravity experiment, in the way that we think of modern experiments, his innovative approach to physics through the synthesis of existing observations led to the creation of a universal theory of gravitation. Newton's understanding of gravity came from his keen observations of both terrestrial and celestial bodies, culminating in the realization that the same force that causes an apple to fall from a tree also governs the motion of the planets and celestial bodies. This idea was revolutionary, as it unified the forces of nature under one universal law. His formulation of the law of universal gravitation became a cornerstone of classical physics, providing the framework for understanding how objects interact with one another in the universe. Although the famous story of Newton's apple falling from a tree is often recounted as a simple anecdote, it was the spark for one of the greatest scientific revelations in history. Legend has it that while sitting under a tree, Newton saw an apple fall, prompting him to question why the apple fell straight down to the earth instead of in another direction. This question led him to consider that the force pulling the apple down was not just a localized force but a universal one, a force that acted on all objects, regardless of their size or position. This moment of insight was the beginning of Newton's formulation of the law of universal gravitation. However, Newton did not immediately conduct an experiment to prove his theory. Instead, he turned to mathematics, using the observations of earlier astronomers and physicists to craft a theoretical model of gravity that would explain the forces acting on objects both on Earth and in space. Before Newton, several scientists had observed the effects of gravity but lacked a cohesive theory to explain its workings. Galileo had demonstrated that objects fell at the same rate regardless of their weight, and Johannes Kepler had formulated laws of planetary motion, but the true nature of gravity remained elusive. Newton combined these previous findings, and through his own work, formulated the three laws of motion and the law of universal gravitation. Newton's key insight was that the force of gravity between two objects is proportional to the mass of the objects and inversely proportional to the square of the distance between them. In mathematical terms, this can be expressed as F equals gm1 m2 r2 F equals g backslash frac or 1 m underscore 2, r squared, F equals gr2 m1 m2, where Ff is the gravitational force between two objects, Gg is the gravitational constant, m1 m underscore 1 m1 and m2 m underscore 2 m2 are the masses of the two objects, and rrr is the distance between their centers. This equation, formulated by Newton, not only described the force that caused objects to fall toward the Earth but also explained how the planets in our solar system orbit the Sun. The law of universal gravitation provided a unified explanation for both terrestrial and celestial phenomena, something that had never been done before. While Newton did not conduct a singular gravity experiment, his theoretical work allowed others to test the principles he established. One of the first successful tests of Newton's theories came from his observations of the Moon's orbit. He realized that the same force that caused an apple to fall to the ground was also responsible for keeping the Moon in orbit around the Earth. By applying his laws of motion and gravitation, he showed that the Moon's motion was governed by the same force as that of falling objects. This idea was revolutionary because it suggested that gravity was a universal force, acting equally on both small objects and massive celestial bodies, and that the motion of celestial bodies could be understood using the same laws as the motion of everyday objects. Newton's work not only answered long-standing questions but also opened up a new realm of scientific inquiry. His laws allowed future generations of scientists to predict the motions of planets, satellites, and even spacecraft. Newton's law of universal gravitation had far-reaching implications for the field of astronomy. By using his laws, scientists could now calculate the orbits of planets, predict the motions of comets, and even determine the mass of celestial bodies. Newton's work paved the way for later advancements in physics, such as Albert Einstein's theory of general relativity. Although Einstein's work replaced Newton's laws in certain extreme conditions, such as near black holes or at speeds close to the speed of light, Newton's laws remain an incredibly accurate approximation for most everyday applications, from the motion of planets to the flight of satellites. In addition to his contributions to physics, Newton's approach to science, relying on observation, mathematical reasoning, and logical deduction, helped establish the foundation for the scientific method as we know it today. His work demonstrated the power of applying a rigorous, systematic approach to understanding the natural world, a legacy that has shaped scientific inquiry for centuries. Newton's theory of gravity is one of the most enduring legacies in the history of science. His work unified various aspects of the physical world under one framework and allowed humanity to understand the motion of the stars, planets, and even the trajectories of objects on Earth. The theory of universal gravitation laid the groundwork for many scientific discoveries in the centuries that followed, including the exploration of space, the development of satellite technology, and the understanding of black holes and the cosmos. Although Newton never conducted a specific gravity experiment, his work stands as a testament to the power of theoretical reasoning and mathematical precision in science. His ability to synthesize knowledge, make groundbreaking connections, and test his theories through observation and calculation marked a pivotal moment in the history of science, and his law of universal gravitation continues to shape the way we understand the universe today. Newton's gravity experiment 1687, unveiling the laws of nature. Isaac Newton, one of the most influential figures in the history of science, made groundbreaking contributions that changed the way humanity understood the natural world. Among his most significant achievements was the formulation of the laws of motion and universal gravitation. His work, especially as laid out in the 1687 book Philosophiae Naturalis Principia Mathematica, Mathematical Principles of Natural Philosophy, fundamentally altered the scientific understanding of gravity. While Newton didn't perform a single gravity experiment, in the way that we think of modern experiments, his innovative approach to physics through the synthesis of existing observations led to the creation of a universal theory of gravitation. Newton's understanding of gravity came from his keen observations of both terrestrial and celestial bodies, culminating in the realization that the same force that causes an apple to fall from a tree also governs the motion of the planets and celestial bodies. This idea was revolutionary, as it unified the forces of nature under one universal law. His formulation of the law of universal gravitation became a cornerstone of classical physics, providing the framework for understanding how objects interact with one another in the universe. Although the famous story of Newton's apple falling from a tree is often recounted as a simple anecdote, it was the spark for one of the greatest scientific revelations in history. Legend has it that while sitting under a tree, Newton saw an apple fall, prompting him to question why the apple fell straight down to the earth instead of in another direction. This question led him to consider that the force pulling the apple down was not just a localized force but a universal one, a force that acted on all objects, regardless of their size or position. This moment of insight was the beginning of Newton's formulation of the law of universal gravitation. However, Newton did not immediately conduct an experiment to prove his theory. Instead, he turned to mathematics, using the observations of earlier astronomers and physicists to craft a theoretical model of gravity that would explain the forces acting on objects both on Earth and in space. Before Newton, several scientists had observed the effects of gravity but lacked a cohesive theory to explain its workings. Galileo had demonstrated that objects fell at the same rate regardless of their weight, and Johannes Kepler had formulated laws of planetary motion, but the true nature of gravity remained elusive. Newton combined these previous findings, and through his own work, formulated the three laws of motion and the law of universal gravitation. Newton's key insight was that the force of gravity between two objects is proportional to the mass of the objects and inversely proportional to the square of the distance between them. In mathematical terms, this can be expressed as F equals gm1 m2 r2 F equals g backslash frac or 1 m underscore 2 r squared F equals gr2 m1 m2, where FF is the gravitational force between two objects, GGG is the gravitational constant, m1 m underscore 1 m1 and m2 m underscore 2 m2 are the masses of the two objects, and RRR is the distance between their centers. This equation, formulated by Newton, not only described the force that caused objects to fall toward the Earth but also explained how the planets in our solar system orbit the Sun. The law of universal gravitation provided a unified explanation for both terrestrial and celestial phenomena, something that had never been done before. While Newton did not conduct a singular gravity experiment, his theoretical work allowed others to test the principles he established. One of the first successful tests of Newton's theories came from his observations of the Moon's orbit. He realized that the same force that caused an apple to fall to the ground was also responsible for keeping the Moon in orbit around the Earth. By applying his laws of motion and gravitation, he showed that the Moon's motion was governed by the same force as that of falling objects. This idea was revolutionary because it suggested that gravity was a universal force, acting equally on both small objects and massive celestial bodies, and that the motion of celestial bodies could be understood using the same laws as the motion of everyday objects. Newton's work not only answered long-standing questions but also opened up a new realm of scientific inquiry. His laws allowed future generations of scientists to predict the motions of planets, satellites, and even spacecraft. Newton's law of universal gravitation had far-reaching implications for the field of astronomy. By using his laws, scientists could now calculate the orbits of planets, predict the motions of comets, and even determine the mass of celestial bodies. Newton's work paved the way for later advancements in physics, such as Albert Einstein's theory of general relativity. Although Einstein's work replaced Newton's laws in certain extreme conditions, such as near black holes or at speeds close to the speed of light, Newton's laws remain an incredibly accurate approximation for most everyday applications, from the motion of planets to the flight of satellites. In addition to his contributions to physics, Newton's approach to science, relying on observation, mathematical reasoning, and logical deduction, helped establish the foundation for the scientific method as we know it today. His work demonstrated the power of applying a rigorous, systematic approach to understanding the natural world, a legacy that has shaped scientific inquiry for centuries. Newton's theory of gravity is one of the most enduring legacies in the history of science. His work unified various aspects of the physical world under one framework and allowed humanity to understand the motion of the stars, planets, and even the trajectories of objects on Earth. The theory of universal gravitation laid the groundwork for many scientific discoveries in the centuries that followed, including the exploration of space, the development of satellite technology, and the understanding of black holes and the cosmos. Although Newton never conducted a specific gravity experiment, his work stands as a testament to the power of theoretical reasoning and mathematical precision in science. His ability to synthesize knowledge, make groundbreaking connections, and test his theories through observation and calculation marked a pivotal moment in the history of science, and his law of universal gravitation continues to shape the way we understand the universe today. Marie Curie's radium research, 1898, pioneering the future of science. Marie Curie, one of the most renowned and groundbreaking scientists in history, forever changed the world of physics and chemistry with her research on radioactivity. Her work in the late 19th and early 20th centuries, particularly on radium, laid the foundation for the study of nuclear physics and the development of modern medicine. Curie's discoveries not only advanced science but also transformed society's understanding of atomic structure and energy. Marie Curie, born Maria Sklodowska in 1867 in Warsaw, Poland, moved to Paris to continue her education at the Sorbonne, where she became one of the first women to earn a degree in physics and mathematics. It was at the Sorbonne that Curie began her pioneering work in the emerging field of radioactivity, a term that she herself coined. Her remarkable achievements were in large part due to her relentless curiosity, her unyielding determination, and her exceptional ability to conduct experiments with precision and care. Curie's path to discovering radium began with her work on the mysterious rays emitted by uranium compounds. In the 1890s, the French physicist Henri Becquerel had discovered that uranium emitted rays that could expose photographic plates, but he could not explain why or how this occurred. Curie, captivated by this phenomenon, took it upon herself to investigate the nature of these rays and their potential sources. Her research led her to a significant breakthrough. In 1898, Curie and her husband, Pierre Curie, began studying the mineral pitchblende, now known as uranite, which was known to contain uranium. The Curies noticed that pitchblende was more radioactive than uranium itself, suggesting that there were other elements present that were emitting even stronger radiation. This discovery was the beginning of a long and arduous journey that would lead to the identification of two entirely new elements, polonium and radium. The Curies worked tirelessly in their laboratory, carefully isolating and analyzing the substances within pitchblende. They faced numerous challenges, not least of which was the difficulty of isolating these new elements from the other materials in the mineral. Their work involved long hours of meticulous experimentation, requiring precise handling of highly radioactive substances. The laboratory itself was often filled with the intense glow of the radioactive elements they were studying, which they could only observe through special darkroom techniques. After months of painstaking effort, the Curies were able to isolate a new, previously unknown element, which they named polonium after Curie's homeland of Poland. This was a major scientific achievement, but their work did not end there. They continued their research, isolating another new element in 1898, radium. Radium emitted a more intense form of radiation than any previously known element, and its discovery marked a monumental step forward in the study of radioactivity. The Curie's discovery of radium was a breakthrough that revolutionized the field of physics and chemistry. Radium's intense radiation was unlike anything scientists had seen before, and its ability to penetrate matter raised important questions about atomic structure and energy. The Curie's work with radium also paved the way for further research into the properties of other radioactive elements, eventually leading to the discovery of many other substances with radioactive properties. While the Curie's work on radium was groundbreaking, it was not without its consequences. At the time of their research, the dangers of radiation exposure were not well understood. The Curies, like many other scientists of the era, worked with radioactive materials without the protective measures that are standard in modern laboratories. Both Marie and Pierre Curie were exposed to high levels of radiation during their experiments, which likely contributed to their health problems later in life. Pierre Curie died in 1906 from a tragic accident, and Marie Curie herself suffered from a number of illnesses, including a form of leukemia, which was attributed to her prolonged exposure to radiation. Despite the dangers of their work, the Curies continued their research, driven by their passion for discovery. Marie Curie's unwavering commitment to science was evident not only in her groundbreaking work on radium but also in her perseverance through personal and professional hardships. She became the first woman to win a Nobel Prize, receiving the Nobel Prize in Physics in 1903 alongside her husband and Henri Becquerel for their work on radioactivity. She went on to win a second Nobel Prize in Chemistry in 1911 for her discovery of radium and polonium, making her the first person to ever win Nobel Prizes in two different scientific fields. Curie's research on radium also had significant implications for medicine. In the years following her discovery, radium became a crucial tool in the development of radiation therapy for the treatment of cancer. The ability to target cancerous cells with radiation offered new hope for patients who had previously been without effective treatments. Although radium's harmful effects were not fully understood at the time, its therapeutic potential was widely recognized, and it played a key role in the development of early radiotherapy treatments. Marie Curie's work with radium and her contributions to the study of radioactivity were instrumental in shaping the scientific landscape of the 20th century. Her discoveries laid the foundation for the modern understanding of nuclear physics and the use of radioactive materials in medical treatments. The Curie's research also helped to usher in a new era of scientific exploration, where the atomic structure and the power of radiation became central to both scientific inquiry and practical applications. Marie Curie's legacy is one of perseverance, innovation, and dedication to the pursuit of knowledge. Despite the hardships and dangers she faced, her work revolutionized the world of science and medicine. Today, Marie Curie is remembered as a trailblazer who changed the course of history with her groundbreaking research on radium. Her discoveries have had a lasting impact on science, medicine, and the understanding of the fundamental forces of nature, cementing her place as one of the greatest scientists of all time. Lavoisier's Laws of Chemistry Experiment, 1789. The birth of modern chemistry. Antoine Lavoisier, often referred to as the father of modern chemistry, made groundbreaking contributions to the field of science in the late 18th century. His experiments and theories revolutionized our understanding of chemical reactions, particularly with regard to the law of conservation of mass, which remains a foundational principle in chemistry today. Lavoisier's work in the 1780s, culminating in his 1789 publication Traité élémentaire de chimie, Elementary Treatise of Chemistry, laid the groundwork for the development of modern chemistry and fundamentally changed how scientists approached the study of chemical processes. Born in Paris in 1743, Lavoisier's early career was diverse, with his formal training in law and administration. However, his true passion lay in science, particularly chemistry. At the time, chemistry was still in its infancy, with many of the ideas and practices of alchemy still prevalent. The study of combustion, for example, was based on the outdated theory of phlogiston, which suggested that substances released a substance called phlogiston when they burned. Lavoisier, however, was determined to understand the actual processes occurring during combustion and other chemical reactions. Lavoisier's approach was scientific and systematic, relying on careful observation, precise measurement, and experimentation. His first major breakthrough came in 1772 when he demonstrated that combustion involved the chemical reaction of a substance with oxygen. This was a direct challenge to the phlogiston theory, which claimed that substances lost a material called phlogiston during combustion. Instead, Lavoisier proposed that burning actually involved oxygen combining with the substance, not the release of phlogiston. To further investigate combustion, Lavoisier conducted a series of meticulous experiments. One of his most famous experiments involved burning a substance in a closed container and measuring the changes in weight. He found that the mass of the substance and the oxygen used in the combustion reaction were perfectly balanced, leading to the conclusion that mass is conserved during chemical reactions. This observation became the basis of what is now known as the law of conservation of mass, a fundamental principle that states that matter cannot be created or destroyed in a chemical reaction. The total mass of the reactants in a chemical reaction is always equal to the total mass of the products, an idea that contradicted the previously held belief that mass could be lost or gained during reactions. Lavoisier's law was revolutionary because it introduced a new way of thinking about chemistry. Prior to his work, many scientists believed that reactions involved the creation or destruction of substances, but Lavoisier's experiments demonstrated that reactions are simply transformations of matter. This was a pivotal moment in the history of science, as it helped to shift chemistry away from mystical explanations and toward a more rational, empirical approach based on observation and evidence. In addition to the law of conservation of mass, Lavoisier also contributed significantly to the understanding of chemical nomenclature. Prior to his work, the names of chemicals were often confusing and inconsistent. In 1787, Lavoisier published a new system for naming chemicals, which provided a standardized method for naming elements and compounds based on their chemical composition. This system helped to organize the rapidly growing body of chemical knowledge and set the stage for future discoveries. Another key contribution of Lavoisier was his work on the nature of respiration. He showed that respiration in animals is similar to combustion in that it involves the chemical reaction of oxygen with food substances, releasing energy in the process. This discovery was groundbreaking, as it connected the processes of combustion and respiration, highlighting the importance of oxygen in both. His work on respiration further reinforced his ideas about the role of oxygen in chemical reactions. Lavoisier's contributions to the field of chemistry were immense, but his work did not stop with combustion and respiration. He also helped to identify and name oxygen and hydrogen, two elements that would become central to the development of modern chemistry. He and his colleagues discovered that water is a compound made up of oxygen and hydrogen, an important insight that paved the way for the study of chemical bonding. Despite the revolutionary nature of his work, Lavoisier faced significant challenges during his career. His ideas, particularly the law of conservation of mass, were met with resistance from those who were still loyal to the old phlogiston theory. However, his meticulous experiments and logical reasoning eventually won over the scientific community. Lavoisier's work had far-reaching implications for many fields of science, including physics, biology, and medicine. His experiments on combustion, respiration, and chemical reactions helped to lay the foundation for modern biology and biochemistry. His system of chemical nomenclature is still used today, and his law of conservation of mass continues to be a fundamental concept in the study of chemistry. Tragically, Lavoisier's career was cut short by the French Revolution. In 1794, he was arrested and executed by guillotine, largely due to his association with the old regime and his work as a tax collector. Despite his untimely death, Lavoisier's legacy lived on, and his contributions to science were recognized long after his passing. Today, Lavoisier is celebrated as one of the greatest scientists of all time, and his work continues to inspire chemists and scientists around the world. Lavoisier's experiments and the law of conservation of mass marked the dawn of a new era in science. His work provided a solid foundation for the development of modern chemistry and helped to establish the scientific method as the primary tool for understanding the natural world. Thanks to Lavoisier's dedication and groundbreaking research, chemistry emerged from the realm of mysticism and superstition into a field grounded in empirical science. 4.0 Mini. Gregor Mendel, an Austrian monk, is widely regarded as the father of modern genetics, thanks to his groundbreaking work on heredity in the mid-19th century. His experiments, conducted between 1856 and 1863, with pea plants, Pisum sativum, led to the discovery of fundamental principles of inheritance that later became known as Mendel's laws of heredity. These laws form the cornerstone of the field of genetics and are still vital to our understanding of how traits are passed from one generation to the next. Born in 1822 in the Austrian Empire, Mendel was initially interested in science, but he faced many challenges on his journey to becoming a scientist. After studying at the University of Vienna, he became a monk at the Augustinian Abbey of St. Thomas in Brunn, modern-day Brno, Czech Republic. While fulfilling his religious duties, Mendel pursued his passion for biology, focusing on the inheritance of traits in living organisms. At the time, the prevailing theory of inheritance was based on the blending theory, which suggested that offspring were simply a blend of their parents' traits. Mendel, however, believed that the inheritance of traits was more orderly and based on discrete factors. Mendel's experiments began with the cultivation of pea plants, a common practice in agricultural science. He carefully chose peas for his study because they had easily distinguishable traits, such as flower color, seed shape, and plant height. Additionally, peas have both male and female reproductive organs, allowing for controlled breeding. Mendel's goal was to determine how traits were passed down through generations and whether there was any regularity to the inheritance of these traits. Mendel conducted a series of controlled experiments over several years, crossing different varieties of pea plants with contrasting traits. For example, he crossed pea plants with round seeds with those that had wrinkled seeds and tall plants with short plants. He then carefully recorded the resulting offspring, counting the frequency of each trait in successive generations. One of Mendel's key insights was the discovery that traits are inherited in discrete units, which he referred to as factors. These factors, now known as genes, are responsible for the inheritance of specific traits. Mendel found that when he crossed plants with different traits, the offspring did not exhibit a blending of the parents' traits, but rather showed one of the parental traits. This led him to propose the existence of two alleles, alternative forms of a gene, for each trait, one inherited from each parent. Mendel's experiments led to the formulation of two key principles. The law of segregation. This law states that each individual has two alleles for each trait, one inherited from each parent. These alleles segregate, or separate, during the formation of reproductive cells, gametes, meaning that each gamete carries only one allele for each trait. When two gametes unite during fertilization, the offspring inherits one allele from each parent. The law of independent assortment. This law explains how genes for different traits are inherited independently of one another. Mendel found that the inheritance of one trait, e.g., seed shape, did not affect the inheritance of another trait, e.g., seed color. This principle holds true for genes located on different chromosomes, which assort independently during the formation of gametes. Mendel's meticulous experiments on pea plants revealed these laws of inheritance, which were revolutionary at the time. However, his work was largely ignored by the scientific community during his lifetime. Mendel published his findings in 1866 in an obscure scientific journal, but his work failed to gain significant attention. It wasn't until the early 20th century that Mendel's experiments were rediscovered by scientists like Hugo de Vries, Karl Correns, and Erich von Tschermak, who recognized the importance of his work and confirmed his findings. Mendel's laws of heredity laid the groundwork for the study of genetics and provided a scientific explanation for how traits are passed down from generation to generation. These principles are still fundamental to the field of genetics today and are used to understand not only inheritance in plants and animals but also human genetics, medical conditions, and the principles of breeding in agriculture. Mendel's approach to experimentation was revolutionary. He used a quantitative and systematic approach, carefully counting the number of offspring with each trait and analyzing the ratios. He analyzed the results using basic statistical methods, which helped him identify patterns in the inheritance of traits. His work marked a sharp departure from the more qualitative and anecdotal approaches that were common at the time. Mendel's research on pea plants also demonstrated the concept of genetic dominance. For example, he observed that in the case of seed shape, the round seed trait was dominant over the wrinkled seed trait. This led him to propose that some alleles were dominant, while others were recessive. A dominant allele would mask the effect of a recessive allele when both were present in an individual, which explained why certain traits appeared more frequently in the offspring. Mendel's work had far-reaching implications, both for the understanding of biology and for practical applications in agriculture. His principles were applied to improve the breeding of crops and livestock, helping to produce better yields and more desirable traits in plants and animals. In the decades following Mendel's rediscovery, geneticists began to study the molecular basis of inheritance, leading to the discovery of DNA and the development of modern genetics. Mendel's work also opened the door to the study of heredity and genetic diseases in humans. Understanding how genes are inherited and how mutations in genes can lead to disease has been crucial in fields such as medicine and genetic counseling. Mendel's laws, combined with the discoveries of modern molecular biology, have enabled scientists to unravel the complexities of genetics and inheritance. In the end, Mendel's work, although largely unrecognized during his lifetime, became one of the most important contributions to the field of biology. His experiments on pea plants revolutionized the study of heredity, and his principles of inheritance continue to shape our understanding of genetics today. Mendel's legacy lives on in the study of genetics, making him one of the most influential scientists in history. In 1905, Albert Einstein revolutionized the field of physics with his theory of special relativity, fundamentally changing our understanding of space, time, and the speed of light. One of the most intriguing and controversial aspects of this theory was its implications for the speed of light and whether it could ever be surpassed. Einstein's work in 1905, often referred to as his annus mirabilis, miracle year, introduced ideas that would change the way we perceive the universe and challenge long-standing assumptions about the nature of reality. Einstein's special relativity theory was based on two key postulates. The first postulate stated that the laws of physics are the same for all observers, regardless of their relative motion. In other words, the laws of physics apply equally to someone standing still and someone moving at a constant velocity. The second postulate, which was the more revolutionary one, stated that the speed of light in a vacuum is constant for all observers, regardless of their motion or the motion of the light source. This second postulate was groundbreaking because it contradicted the common assumption of the time that speeds could simply add up. For example, if you were in a moving car and threw a ball forward, the speed of the ball would be the speed of the car plus the speed of the throw. However, light didn't behave this way. According to Einstein, no matter how fast an observer moved, they would always measure the speed of light in a vacuum as 299,792 km per second, or approximately 186,282 miles per second. This was a radical departure from classical mechanics, where speeds could be added together. The implications of the constant speed of light were profound. It meant that time and space were not absolute, but interconnected and could change depending on the observer's motion. This led to the concept of time dilation, where time appears to pass slower for an object moving at high speeds relative to a stationary observer. Similarly, length contraction stated that objects moving at speeds close to the speed of light would appear shorter in the direction of motion. These ideas seemed strange, but they were mathematically consistent and eventually confirmed by experimental evidence. Einstein's theory also led to the famous equation E equals mc2 E equals mc caret 2 E equals mc2, which describes the relationship between energy, E, mass, m, and the speed of light, c. This equation showed that mass and energy are interchangeable, implying that a small amount of mass could be converted into a vast amount of energy. This principle became the foundation for the development of nuclear energy and has had far-reaching implications in fields ranging from astrophysics to particle physics. As for the possibility of surpassing the speed of light, Einstein's theory strongly suggested that this was impossible. According to special relativity, as an object approaches the speed of light, its mass increases, and it requires more and more energy to continue accelerating. To reach the speed of light would require an infinite amount of energy, which is clearly unattainable. This made the idea of surpassing the speed of light appear physically impossible, at least within the framework of special relativity. Despite this, the question of faster-than-light, FTL, travel and communication has fascinated scientists and science fiction enthusiasts alike for over a century. In the years following Einstein's theory, researchers explored various theoretical possibilities for FTL travel, such as wormholes, the Alcubierre drive, and the manipulation of spacetime. However, these ideas remain speculative and far from practical application. The concept of the speed limit set by light has had profound consequences for our understanding of the universe. It implies that nothing can travel faster than light, creating a cosmic speed limit that governs all motion. This limit is crucial for the structure of causality, which dictates that cause must always precede effect. If information or objects could travel faster than light, it could potentially lead to paradoxes, such as time travel to the past, which would undermine our understanding of the fundamental nature of time. Despite the challenges and limitations posed by special relativity, the theory has been remarkably successful in explaining a wide range of physical phenomena. It has been confirmed by numerous experiments, including the observation of time dilation in particles moving close to the speed of light and the detection of gravitational waves. Special relativity has become a cornerstone of modern physics, providing the foundation for much of our understanding of the universe, from the behavior of subatomic particles to the dynamics of galaxies. In conclusion, Einstein's theory of special relativity, and the concept of the speed of light as an unbreakable barrier, transformed our understanding of space, time, and the fundamental nature of the universe. While the idea of traveling faster than light remains a tantalizing dream for some, Einstein's work has shown that the speed of light is not just a measure of how fast light travels, it is a fundamental constant that shapes the very structure of reality itself. The theory of special relativity remains one of the most important scientific achievements of the 20th century, and it continues to inspire scientific inquiry and exploration to this day. Pavlov's conditional reflex experiment, 1900s. In the early 1900s, Russian physiologist Ivan Pavlov conducted a series of groundbreaking experiments that would forever change the field of psychology. His research into the digestive systems of dogs led to the discovery of what we now know as classical conditioning, a theory that explains how certain behaviors can be learned through association. Pavlov's experiment became a landmark in the study of behaviorism and laid the foundation for understanding how environmental stimuli can influence human and animal actions. Pavlov initially began his work with a focus on digestion, studying the salivary glands of dogs. He observed that when dogs were presented with food, they naturally salivated in response. Over time, Pavlov noticed that the dogs began to salivate even before the food was placed in front of them. They would start salivating as soon as they saw the lab assistants who usually fed them or heard the sound of footsteps approaching. This observation puzzled Pavlov and led him to a series of controlled experiments to understand the phenomenon. In his famous experiment, Pavlov paired a neutral stimulus, such as the sound of a bell, with the presentation of food. Initially, the sound of the bell alone did not cause the dogs to salivate. However, after several repetitions of pairing the bell with food, the dogs began to salivate just in response to the sound of the bell, even when no food was presented. The dogs had learned to associate the sound of the bell with the arrival of food, and this association triggered an automatic, conditioned response, salivation. Pavlov's work demonstrated that organisms could learn to associate neutral stimuli with significant events. In this case, the bell, which initially had no inherent meaning to the dogs, became a signal that predicted the arrival of food. The dog's salivation in response to the bell was no longer a natural, unconditioned reflex, it had become a conditioned reflex, learned through the process of association. This discovery had profound implications for the study of behavior and learning. It showed that behavior could be shaped by the environment, and that stimuli in the environment could trigger automatic responses without the need for conscious thought. Pavlov's findings laid the groundwork for behaviorism, a school of thought that dominated psychology in the early 20th century and emphasized the role of external stimuli in shaping behavior. Pavlov's experiment also highlighted the idea of stimulus generalization, where a response learned to one stimulus could be triggered by similar stimuli. For example, the dogs that had been conditioned to salivate at the sound of the bell might also salivate in response to a similar sound, such as a buzzer or a whistle. This demonstrated that the conditioned response could be generalized to similar stimuli, extending the range of behaviors that could be influenced by environmental cues. Pavlov's work also led to the development of the concept of extinction, which occurs when a conditioned response gradually fades away if the conditioned stimulus is repeatedly presented without the unconditioned stimulus. For instance, if the sound of the bell was repeatedly presented without food, the dogs would eventually stop salivating in response to the bell, as the association between the bell and food was no longer reinforced. Extinction demonstrated the dynamic nature of learned behaviors and how they could be undone through the absence of reinforcement. In addition to its influence on psychology, Pavlov's research has had broad applications in various fields, including education, advertising, and therapy. Classical conditioning principles have been used to help treat phobias, as well as to develop methods for modifying undesirable behaviors. In education, the principles of reinforcement and punishment based on conditioning have been applied to shape students' behavior and promote learning. Pavlov's discovery of classical conditioning also opened the door for later psychologists, such as John B. Watson and B. F. Skinner, to further explore the role of environmental stimuli in shaping behavior. Watson, in particular, applied Pavlov's principles to human behavior and conducted his own famous experiments, such as the Little Albert experiment, which demonstrated that emotional responses could be conditioned in humans as well. Overall, Pavlov's experiment on conditioned reflexes had a profound and lasting impact on the field of psychology. It provided a scientific basis for understanding how behaviors are learned and shaped by environmental influences. His work also helped to establish behaviorism as a dominant theory in psychology and paved the way for future research on learning and conditioning. Even today, Pavlov's findings continue to influence the way we understand human and animal behavior, from the treatment of psychological disorders to the study of consumer behavior. 4.0 Mini. Beck's Depression Inventory, 1960s. In the 1960s, American psychiatrist Aaron T. Beck developed a groundbreaking tool for assessing the severity of depression. Known as the Beck Depression Inventory, BDI, this self-report questionnaire was designed to measure the intensity of depressive symptoms in individuals, helping clinicians diagnose depression more effectively and understand its impact on a person's mental state. Beck's contribution to the field of psychology revolutionized how depression is identified and treated, making it one of the most widely used tools in both clinical settings and research. Beck, who had been researching depression for years, noticed a significant gap in the ability to quantitatively assess the mental state of patients suffering from the disorder. Traditional methods of diagnosis often relied on vague and subjective criteria, which made it difficult to measure the progression or severity of depression in patients. Beck's goal was to create a standardized and reliable tool that could provide an objective measurement of depressive symptoms. His work stemmed from his theory that negative thoughts and distorted thinking patterns play a key role in the development and persistence of depression. The Beck Depression Inventory, first published in 1961, consisted of a series of 21 multiple-choice questions, each designed to assess a specific symptom or experience related to depression, such as mood, guilt, self-esteem, sleep patterns, and physical symptoms like fatigue. Each question was scored on a scale of 0 to 3, with higher scores indicating more severe symptoms. The questions were structured so that patients could rate their feelings over the past 2 weeks, providing a snapshot of their emotional state and helping clinicians gauge the level of depression. The BDI was revolutionary in several ways. First, it provided a standardized, quantifiable approach to understanding depression. The tool allowed for a more consistent evaluation of depression severity across different patients and clinical settings. Second, it helped shift the focus of diagnosis from vague psychological theories to concrete, observable symptoms, making it easier for clinicians to monitor changes over time. Third, the BDI's self-report format empowered patients to actively engage in their own assessment, creating an important opportunity for self-reflection and communication with their therapist or doctor. In the years following its creation, the BDI became widely accepted as one of the most reliable and valid tools for measuring depression. Its ease of use and ability to capture a range of depressive symptoms made it an essential part of clinical practice, and it was often used in both inpatient and outpatient settings to monitor patient progress during treatment. The BDI was particularly helpful in assessing changes in depression levels over the course of therapy or after the introduction of antidepressant medications. One of the key aspects of Beck's Depression Inventory was its ability to differentiate between different levels of depression. A score on the BDI could range from minimal depression to severe depression, allowing clinicians to determine the most appropriate course of treatment. This range of severity was especially valuable for doctors, as it provided a more nuanced understanding of the patient's mental health and could guide decisions regarding treatment intensity. The BDI also became an important research tool in psychology and psychiatry. Researchers used the inventory to assess the effectiveness of various therapeutic interventions, medications, and other treatments for depression. It allowed them to track symptom changes in large groups of patients, providing valuable data for scientific studies on depression and its treatment. As a result, the Beck Depression Inventory played a significant role in advancing the understanding of depression as a medical condition and in developing more effective therapies. Over time, the Beck Depression Inventory was revised and updated. The original version was followed by the BDI-2, which was released in 1996 to align with the latest diagnostic criteria for depression, as outlined in the DSM-IV, Diagnostic and Statistical Manual of Mental Disorders. The updated version included changes in the wording of some questions and added items to reflect the evolving understanding of depression and its symptoms. Beyond its use in clinical settings, the Beck Depression Inventory has had broader societal implications. It helped reduce the stigma associated with mental health by providing a scientific, measurable way of assessing depression. By making the experience of depression more visible and understandable, the BDI contributed to the ongoing effort to normalize mental health discussions and ensure that individuals receive the support and treatment they need. Today, Beck's Depression Inventory is considered one of the gold standards for assessing depression and is used widely across the world. It has not only helped countless individuals receive accurate diagnoses and appropriate treatment but has also paved the way for other mental health assessments. Beck's work on the BDI helped to establish him as a leading figure in the study of cognitive therapy and depression, and his contributions continue to shape the field of mental health today. In summary, Aaron Beck's Depression Inventory revolutionized the understanding and treatment of depression by providing a reliable, objective, and accessible tool for measuring depressive symptoms. Its development marked a significant milestone in the field of psychology, making it possible to diagnose and track depression with greater accuracy and consistency. As a result, Beck's work has had a lasting and profound impact on how depression is perceived and treated in both clinical practice and research.